So hi everyone and welcome to this video on deriving the betas in a bivariate CLRM setting. So for this particular video, we're going to derive the model intercept and the slope coefficient in at least a bivariate form, and we'll see how we can do that by just using the first order conditions from this unconstrained minimization process of the OLS. So if you recall, the postulation that OLS makes is that to get the estimators, we minimize the residual sum of squares. So to get the residual sum of squares, that's just the sum of I is equal to 1 until n of your residual, which say is epsilon I squared, right? Because it's residual sum of squares. But we know that epsilon is just equal to yi minus beta naught hat minus beta 1 hat x sub I squared. So essentially, we're minimizing this particular function here. Okay, so what we need to do is we need to minimize this function. Let's call it f. And it just so happens that this function is a function of both beta naught hat and beta 1 hat. Okay, so we're going to essentially use these two first order conditions and equate this to 0. We use this one to solve for beta naught hat, the optimal one, and this one to solve for beta 1 hat, the optimal one. So we're going to use these FOCs to derive what ends up being the value of beta 0 and beta 1. Okay, so let's derive beta 0 first. So if you recall, again, the function goal, okay, the function is f beta 0 hat, beta 1 hat. The goal is to minimize the sum I equals 1 to n, okay, of the residual sum of squares, which is yi, minus beta naught hat minus beta 1 hat x sub I squared, right? So if we derive, okay, deriving the model intercept. Okay. So what we do is first, okay, we use the derivative. So that's the partial derivative of the function with respect to beta 0, right? So what do we get? Okay, so if you look at the function, okay, you have an exponent raised to 2. So we can use chain rule. So that's 2 summation I is equal to 1 to n y sub I minus beta naught hat minus beta 1 hat x sub I. So we're deriving with respect to beta naught. So what's the coefficient of beta naught? And that's -1. So we multiply this by -1. And we get -2 summation I is equal to 1 to n y sub I minus beta 0 hat minus beta 1 hat x sub I. Then what we can do is we can sort of distribute the -2 and the summation around. So notice is equal to 0. We're equating to 0. So 0 is equal to -2 summation I is equal to 1 to n y sub I, okay, plus 2 beta 0 hat, because all parameters beta 0 and beta 1 come before the summation sign. You don't sum those up. So you do sum I is equal to 1 to n, okay, that plus, because minus times a minus is a plus, plus 2 beta 1 hat summation I is equal to 1 to n x sub I. Okay, so we have that one there. Now we can easily get a few more things. Okay, so notice everything there has a 2 there, so we can just take it out. So divide everything by 2. So we get 0 is equal to negative sum I is equal to 1 to n y sub I plus beta 0 hat sum I is equal to 1 to n plus beta 1 hat sum I is equal to 1 to n x sub I. Okay, that's what we have. Now, there are a couple of formulas that we need to be aware of. So if we just have this summation, sum of I is equal to 1 to n, it's just essentially summing up all your i's, right? And essentially, if you sum up all your i's, it's just summing up all your observations. So this summation is just equal to n. It's just equal to n. Now, if you recall, the formula for the mean of x, which is x bar, is just equal to the sum of I is equal to 1 to n of x sub I. So you sum up all of the observations x's divided by the total number of observations n. So if you want to compute directly for the summation, which is sum of I is equal to 1 to n x sub I, that's just equal to n x bar, right? That's just the same. Now, the third one is that if we have y bar, the mean of y, this is again equal to sum I is equal to 1 to n of y sub I divided by the total number of observations n, right? That's how to get the mean of y. If you want to get just the summation, then the summation I is equal to 1 to n of y sub I is just equal to n y bar. So essentially, we can use those three forms there that we derived to plug it into what we have in our solution so far. So from here, okay, so we get 0 is from here, 0 is equal to sum of y sub I. So that's just ny bar. So this is negative n y bar plus beta 0 hat. Notice this is just a summation, so that's just equal to n. Then we have plus beta 1 hat. Okay, sum of x sub I, that's just n x bar. Okay, now notice every term here has an n, so we can divide everything by n. N, that cancels out. And we get 0 is equal to negative y bar plus beta naught hat plus beta 1 hat x bar. And all we need to do is we just need to isolate out beta naught hat. So beta naught hat is equal to y bar minus beta 1 hat. Oops. Minus, so that's y bar minus beta 1 hat x bar. And this is your form for the model intercept, right? So this is how beta naught is computed for. So if you use software to do this quickly, the formula for beta naught would be this one. So this is the model intercept, okay? So beta naught hat is equal to y bar minus beta naught hat x bar. So what we do now is since we have the model intercept, we can derive the slope coefficient. So let me write a new sheet here. So recall the function again. Let me just rewrite. Is equal to, we're going to minimize the residual sum of squares. Sorry for that. RSS. So that's minimum. Y sub I minus beta naught hat, beta 1 hat, x sub I squared. Okay, so now instead of deriving with respect to beta 0, we derive with respect to beta 1. So beta naught hat, 1 hat, derive with respect to beta 1 hat. So this one should be equal to, okay, again, chain rule. That's 2. Sum I is equal to 1 to n, y sub I minus beta naught hat minus beta 1 hat, x sub I, right? But we need to derive the thing inside. So we're now deriving with respect to beta 1. So what's the derivative of the function inside with respect to beta 1? That's just negative x sub I, right? So we can simplify. So that's negative 2 x sub I. Sum I is equal to 1 to n, y sub I minus beta naught hat minus beta 1 hat x sub I. Okay, so we have that there. Then like before, we can distribute. So 0. So 0 is equal to negative 2 summation I is equal to 1 to n x sub I y sub I plus 2 beta 0 hat sum I is equal to 1 to n of x sub I plus 2 beta 1 hat summation x sub I squared, right? Because we have now x sub I and then an x sub I there. So multiply, it becomes a squared. Okay, so we have that form there now. Now, notice everything has a 2. So we can just divide everything by 2. Takes out the 2. So we get 0 is equal to summation I is equal to 1 to n x sub I y sub I plus beta 0 hat sum I is equal to 1 to n x sub I plus beta 1 hat sum I is equal to 1 to n x sub I squared. So that takes out to 2. Now, we have a beta naught here, but remember, okay, we solve for beta naught. Beta naught hat is equal to y bar minus beta 1 hat x bar, right? So we can plug that in. 0 is equal to sum I is equal to 1 to n x sub I y sub I plus, okay, we're gonna plug it in. So this becomes y bar minus beta 1 hat x bar. Okay, we're just plugging it in to 1 to n x sub I plus beta 1 hat sum I is equal to 1 to n x sub I squared. Okay, so we have that there. Then what we do now is we sort of distribute the summation. So this is 0. Sum I is equal to 1 to n x sub I y sub I, right? Plus y bar. The mean comes before the summation sign. So you have sum I is equal to 1 to n x sub I minus beta 1 hat x bar sum I is equal to 1 to n x sub I. Okay. Then just copy the last term. Beta 1 hat sum I is equal to 1 to n x sub I squared. Okay. Then remember, we had a couple of identities we discussed. So nx bar is just equal to sum I is equal to 1 to n x sub I. Then you have ny bar, that's sum I is equal to 1 to n y I. So we can apply that here. So you get 0 is equal to sum I is equal to 1 to n x sub I y sub I plus, note this one is nx bar, right? So this is n x bar y bar, the y bar remaining there, minus you have here this one, this is nx bar again. So you have beta 1 hat nx bar squared, right? You have now 2 x bars there. Then the last term remains the same, beta 1 hat sum I is equal to 1 to n x sub I squared. Okay. Now what we do is all the terms, okay, all the terms, oops, we forgot the negative sign here. So all of these should have a negative. What we do now is all the terms with beta 1, we put on one side. So for example, this is, let me transpose this one. So that's beta 1 hat nx bar squared. Let me just make the transpose easier. I is equal to 1. Okay, so what I do from here is I transpose this one to the other side and this one to the other side such that everything is just with respect to beta 1 here. So I get sum x sub I y sub I minus n x bar y bar is equal to beta 1 hat. So I'll put the positive thing first. Sum I is equal to 1 to n x sub I squared minus n x bar squared, right? Then what I do to isolate out beta 1 is to just divide both sides by this thing. So sum I is equal to 1 to n x sub I squared minus n x bar squared. So I get beta 1 hat is equal to sum x I is equal to 1 to n xi yi minus nx bar y bar all over sum I is equal to 1 to n x sub I squared minus nx bar squared. And this is the derivation of your slope coefficient term. And if you recall, the numerator, this form here, if you recall your elementary statistics, so that's actually equal to the covariance of x and y. And the denominator is exactly the variance of x. Right? So that's what we have there. Okay, so we're gonna go further in our discussion, such as a few properties of the CLRM, and that will happen in the next video. So for this video, we just derived the slope coefficient and the model intercept. So thank you for your attention, and I'll see you in the next video. Thank you very much.